SwayamPrabha. Digital India. Educated India.
Hello, welcome to Introduction to Composites. Today is the 5th day of the ongoing week and we have been discussing different wet processing methods for thermoset composite materials. Today we will discuss two more or possibly three more different types of processes which are wet in nature and which are applicable to thermoset composites. And the first process we are going to discuss will be RTM, which is a short form for resin transfer molding. So, a limitation of the vacuum bag molding or bag molding processes is that the fibers, when you apply a lot of pressure, they tend to dislodge from their original position, and there is a chance that the orientation of the fibers in the system, especially if you use pressure, external pressure, may not be same as what you intended, because as you apply external pressure, the fluid in the thing flows at a higher velocity with high pressure and it tends to change the orientation of the fibers. So, RTM is one method which helps us produce good quality composites in a way that the fibers do not get overly dislodged from their original position. So, let us look at this picture as to how the composite material is produced in the RTM process. First thing which we have is a bottom part. So, let us say this is the bottom part of the mold. So, this can be made of metal or some strong plastic which can take a lot of temperature and things like that. And then of course, on top of this mold you put all the release agents and the gel to ensure a good finish. And once you are done with that, then you on top of it you put the fibers. But in RTM you do not put prepregs. So, we do not use prepregs in RTM, we use dry fibers and we put all the layers. So, suppose there are 10 layers, we put all the 10 layers in step by step, but between two layers we do not put any matrix, we just deposit all the layers in the intended orientation and sizes, and that is all we do. So, these are fibers or rather better will be fiber layers, and this is our bottom part of the mold. Bottom part of the mold. And then what we do is we have a top part. So, you can call it top part of the mold. So, let us say this is the top part of the mold. And of course, there is a gap between the top part and the bottom part, and we clamp. Now, in this picture I have made the bottom part very thick, but anyway the point is that we clamp the top part and the bottom part using some sort of a mechanical device. So, this is my clamp. So, we clamp it all around and we have a similar clamp on this side. So, what this ensures is that everything remains in orientation and things do not move. And of course, from the top part we have, there is some gap between the bottom and the top and there is air in there. So, we have an outlet for air and this we connect to vacuum. Okay. But we have still not shown how the matrix get added, and this is where, so the matrix is injected in this mold once all the layers have been put through some outlet. So, this may be the path for matrix material, resin. So, resin is injected and it is injected at a pressure, but the pressure is not very high in the sense that when this resin flows through the fibers, it does not flow at very high velocity, it flows relatively slowly at modest pressures, and as a consequence the fibers do not get disoriented from their original configuration. And to ensure that, we make sure that whatever resins we use, they have low viscosity. Okay. So, you mix the resin with the hardener and you inject, and this resin with the hardener should have low viscosity, only then it will flow easily through all the network of fibers. It wets everything, and of course, this is assisted, there is also a vacuum to remove all the air, and once it has wetted everything, then you apply heat and you do not apply a lot of pressure, okay, and in that state you let it cure. So, as a consequence, you get a high quality, high finish product. Of course, finish is on top side and bottom side with low porosity, and also the fibers are not disoriented more than what can be tolerated. So, this is all about RTM. Now, I had said that there is a special version of RTM known as VARTM, and this is vacuum assisted RTM. So, in vacuum assisted RTM, it is the same thing, but you do not send the resin at high pressure, you just slowly let it flow, you do not inject it at high pressure. You only rely on vacuum to draw the resin, and as a consequence, the orientation of the fibers is even better, it is even better. But then you have to make sure that the viscosity of the fluid is extra low, so that it flows nicely and smoothly and it wets everything. So, this is resin transfer molding. The second process we are going to discuss is filament winding. This is filament winding. I think the best way to explain this filament winding is by seeing a picture, because then you will get a very clear idea of how this thing is done. So, this is a schematic which talks about filament winding. Now, what you have here are a large number of fiber rolls, and this entire set is known as a creel. So, you have a creel in which you have different rolls of fibers. Okay. So, filament winding is typically used to produce structures or objects which are axisymmetric, Okay. So, you have fibers coming from creel, and at the other end you have a mandrel. So what is a mandrel? It's basically, so suppose you want to make a pipe, then what do? You have a hollow rod or a shaft, and on top of that you can wind the fiber, and if you can then later somehow remove the shaft from the center, then you have a hollow pipe made up of composite. Okay. So that is what the principle. So the mandrel is something which is axisymmetric in nature, and it is made in a specific way such that it can be very easily removed. So how do we make a mandrel? We can make it from collapsible structures. Collapsible structures. So once the thing is done, then the inner mandrel collapses. It can be made of wood or metals, but which collapses at some specific locations, and then everything falls apart and only the outside thing is left. Or you can make it from low melting point alloys. So low melting point alloys in the sense that its melting point should be less than the decomposition temperature of the composite. Okay. Or you can make it from some salts, eutectic salts, or from some plasters which are either soluble or they are breakable, they are easy to break. Okay. So these things, or you can make it from some inflatable materials. So for instance, you have a stiff rubber and you inflate it, and then on that inflated structure you wind, and then later you deflate it, so internal stuff goes away. Okay. So this is how you make the mandrel, and mandrel, the shape of the mandrel, the cross section of the mandrel decides the cross section of the final product. Okay. So what do? So you have fibers coming from different reels, and they pass through a tub of resin. They pass through a tub of resin, so they become wet, and then they are pulled by this mandrel which is rotating. They are pulled by this mandrel which is continuously rotating. So the fibers wind around the mandrel, and as this is happening, this tub of resin, it moves back and forth. So you start depositing materials along the length of the entire mandrel. Okay. So in this way you can have an axisymmetric structure which is made up of continuous fibers. So here the trick is that you have to use continuous fibers. You cannot have this with short fiber short fibers, and you use this, and you can have this fiber winding in different patterns. So suppose this is, so you can have fibers which are wound like this. Okay. When will this happen? This happens when the tub of resin's velocity is extremely small. If it is extremely small, then the fibers which will wind around the mandrel will be more or less at 90 degrees to the axis of the mandrel. Okay. So this is called hoop winding or circumferential winding. Hoop winding or circumferential winding. Another way you can have winding is at an angle. So you can have different angles, and so this is angular or helical, and this angle, so if this is the axis of the mandrel and this angle theta, this theta can be controlled by controlling two parameters. And what are those two parameters? So theta is a function of RPM and this velocity v, these two things. Okay. So if the RPM is extremely high, this angle will be closer to 90 degrees. If this RPM is very slow and velocity is very high, this angle will be closer to 0 degrees. So this can be mathematically controlled, okay, based on geometry. So you can have hoop winding, helical winding, or you can have even a longitudinal winding. Now in longitudinal winding the fibers are like this, but of course you can never have fibers exactly at 0 degrees, but you can get close to that, because at 0 degrees it means that mandrel is not moving, but it has to move, otherwise the fibers won't get deposited. So this is there, okay. So you can have maybe in the inner surface fibers, so this is longitudinal. So you can have different layers of fibers. Some fibers could be at 45 degrees, some could be at 90 degrees, some could be at 0 degrees. Based on what your structural needs are, you can have this. So what is happening is that once all the fibers have been wound and there is tension in the fibers, so it is tight, right, it is tight, and also there is not a lot of air in this system, then you somehow expose it to heat and you let it cure. So this is what filament winding is all about. There are a couple of limitations of this process, and also there are a couple of advantages. So let us look at some of these limitations and advantages of filament winding process. So the first, so let us look at some of the advantages. Okay. So it is, you can automate it easily. It is not a very complicated setup, okay. The second thing is that the products which come out of it are of high strength, because the fibers in it are in tension, and so they are not loose in the matrix, and there is little air in the system. You can have different sizes using the same setup. You can have a small part, you can have a large part, you can have parts of different cross sections as long as they are symmetric, axisymmetric. So different parts. Sizes and shapes, all you have to do is change the mandrel. And you can have layer by layer control of fiber orientation. Limitations. What are the limitations? Limitations are 0 degrees and 90 degrees, difficult to achieve. And 0 degrees is longitudinal, okay, and longitudinal is more difficult compared to 90 degrees. The second thing is, all axisymmetric parts may not be easily producible. So for instance, you can produce parts which look like this, but suppose I have to produce a part which is like this. Excuse me. So this is an axisymmetric part, but suppose I have to make a part which is something like this. This is not easy to produce. I can make a mandrel and I can wind it, that is not a problem, but taking out the mandrel becomes tricky, because the mandrel will get stuck, okay. So producing such parts are not easy to produce. So reverse curvature parts. Not easy to produce, okay. The other one is that surface finish. is not always great. It's not always great. So, these are some of the limitations of these parts. So, you can use this process either for using fibers, I mean I am talking about continuous fibers, or you can use this process either also if you have tapes, that also you can do. And these tapes could be just fibers or even prepregs. If it is a prepreg, it does not have to go through the bath of matrix, right? It does not have to go through matrix bath. Okay. So, this is about filament winding. And the last production method we will discuss today is known as pultrusion. So, this pultrusion is also used quite a bit for thermoset plastics. So, what happens in pultrusion? Okay. So, actually using pultrusion you can make two types of composites. One is with short fiber, composites, and the other one is with, and the methods are different, continuous fiber composites. The short fiber composites which are produced when we use this pultrusion process are typically thermoplastics, and we will understand it later why. And these continuous fiber composites which are typically made from pultrusion process, they are typically thermosets. So, we will first discuss A and then we will discuss B. Okay. So, how do we use pultrusion as a process to produce short fiber composites? So, what do we use this these type of composites? So, typically we use this process to produce bars, okay, tubes, rods and stuff like that. Basically in all these members the cross section of the material of the part does not change with length. So, you can have pipes, okay. So, you can have different types of sections. So, you can have a cross section like this, okay. You can have a box cross section, and how it is produced we will discuss that. You can have a I cross section, you can have a C cross section, you can have some other types of cross sections like this. Okay. So, in our mechanical engineering courses you may have heard of a method known as extrusion. Okay. So, what happens in extrusion is that you have a tool which has a cross section like the one which is of the final product, and you push the material through that tool, and at the other end you pull the material. So, you have a tool which has a circular cross section, right. So, the material can come out from these holes, everything else is closed, and you push the material from this side and from this side you pull it. So, you get a tube like this. Okay. So, similar, so this is the extrusion process, this is the extrusion process. So, this is used typically in metals. In pultrusion, so in metals you actually push the material, you do not pull it from the other side. Most of the force is applied on pushing the material through the orifice of the right cross section. In pultrusion, rather than pushing, you do not push it, you actually pull it, that is why it is known as pultrusion. So, in case of short fiber composites, so we are still discussing A, short fiber composites. Okay. So, in case of short fiber composites, what the raw material are pellets. Okay. And these pellets have fibers, short fibers. So, these are all pellets and they are surrounded by matrix, and this is what. So, these are all pellets, they are surrounded by matrix, they are separate, and so this matrix is thermoplastic matrix. So, it is a thermoplastic polymer, and these short fibers, so this is my short fiber, this short fiber is, lot of times it may be glass, sometimes maybe it may have some other fibers. So, each pellet has some short fibers in it bound by matrix. So, what you do is you melt all this and then you push it through a hole, you push it through a hole of the right cross section, and as it comes out it becomes somewhat solid and you keep on pulling it, and that is how this pultrusion process happens for short fiber composites. Okay. For long and continuous fibers it is a little trickier, okay, because here short fiber basically you are pushing this material through this flowy thing through a hole, and then as it comes out it becomes cold, so it has some form and you pull it. For long fiber the process is a little more complicated, and we will see a picture so that we understand it better. So, this is the schematic for the pultrusion process. So, what you have here is you have all these reels of fiber, and these reels produce have continuous fibers, and this entire set is known as creel, and these fibers go through a bath of resin, so they become wet. Okay, and this resin, and then there is some tool to remove extra resin, so it swipes off extra resin, and all these fibers then collectively go through a tool which gives it the right shape, and as it comes out at the other end it is having that shape, but it is still very soft and flexible. So, it goes through a heated die. In the heated die it actually gets pressed and at high elevated temperature, and the form is assumed, and then as it comes out it has solidified. It may still be not totally cured, but it has sufficient amount of stiffness so that it can be pulled. So, you keep on pulling it from here using these rollers, and as it comes out it acquires that shape, and this process continues. Okay. So, in this case the fiber is aligned with the length of the cross section, In short fiber composite the fiber is not necessarily aligned with the direction of the pipe or the cross section, but in long fiber continuous fiber composites the length of the part and the length of the fiber, they are aligned. So, this is the pultrusion process, and this essentially concludes our discussion on different ways for manufacturing thermoset composites. Tomorrow we will discuss some other ways, but not necessarily related to thermosets, but related to thermoplastics and other types of composites. So, that concludes our discussion, and we will meet once again tomorrow to complete this discussion on different production processes associated with composites. Thank you.